there are significant gaps and a lack of rigorous mathematical support when it comes to understanding our universe. At the heart of our current knowledge lies a profound paradox. On one side stands quantum physics, a precise and detailed guidebook describing the behavior of tiny particles and the fundamental forces through which they interact. On the other side waits general relativity, equally successful in explaining how matter and energy shape the curvature of space and the flow of time, influencing how both evolve in each other's presence. Each theory excels in its own domain, yet the moment we attempt to use them together, contradictions emerge and the mathematics becomes deeply confusing. For more than a century, physicists have sought a theory of everything, an overarching framework that can reconcile this puzzling tension between quantum mechanics and general relativity, while also unifying all known particles, forces, and interactions into a single, elegant equation. String theory emerged as one of the most promising candidates for this ultimate unification. It proposes that at the most basic level, all constituents of the universe, everything we see around us, are composed of minuscule, vibrating strings of pure energy. While quantum theory has long asked what the fundamental, indivisible building blocks of nature might be, string theory's answer is both simple and revolutionary. Replace the familiar notion of point-like particles with tiny vibrating filaments, much like the vibrating strings on a musical instrument. Just as a cello's vibrating strings can create a spectrum of musical notes, these energy strings can vibrate in myriad patterns, producing the full menagerie of particles that form the tapestry of our world. If correct, this perspective offers a dazzling new vision of the universe at its smallest scales, revealing a veritable orchestra of vibrating strings responsible for every aspect of matter and force. What makes this picture so compelling is that it unites matter particles, such as electrons and quarks, and force-carrying particles, such as photons and gravitons, under one conceptual umbrella. In doing so, string theory aspires to form a harmonious, unified view of reality, a grand synthesis where all that exists emerges from different vibrational patterns of the same fundamental entities. However, there is a catch. The mathematics of string theory does not neatly fit into the familiar three-dimensional space we experience, nor can it function properly in a universe with just 4, 5, or even 6 dimensions. Instead, it dictates that we must consider at least 10 spatial dimensions, plus 1 dimension of time, making for a total of 11 dimensions. According to the theory, these extra dimensions are not merely theoretical constructs, they are as real as the dimensions we inhabit. The difference lies in their scale and geometry. They are thought to be tightly curled, compacted into intricate shapes so small that we cannot detect them with the naked eye or even with our most powerful scientific instruments. Still, these extra dimensions might leave a subtle imprint on the universe we can observe. One avenue of exploration involves high-energy particle collisions, such as those studied at the Large Hadron Collider, LHC, in Geneva, Switzerland. If extra dimensions exist and have the right properties, energetic debris produced by colliding protons might momentarily slip into these hidden dimensions. The result could be a detectable loss of energy from our familiar three-dimensional space, offering a smoking gun signal of their existence. Thus far, such evidence has not appeared, but the possibility remains tantalizing. String theory's downfall, in the eyes of its critics, has been its lack of testable, experimentally verified predictions. Decades of research have not yet yielded definitive proof that the theory describes our reality. Some voices wonder if the field is dead, questioning whether we have spent too long barking up the wrong tree, rather than admitting that nature may not bend to our philosophical predisposition for a singular, all-encompassing explanation. Yet from another perspective, the absence of direct experimental confirmation does not automatically spell failure. Science often progresses through periods of slow, painstaking exploration. As a field matures, it should be judged by its ability to deepen our understanding of fundamental concepts, refine its mathematical structure, and explore new theoretical avenues. By these measures, string theory remains a vibrant and evolving field. It has helped us think more deeply about quantum gravity, the nature of space and time, and the fundamental relationships among the particles and forces we know. It is wise to remain open-minded, acknowledging that there may be other, entirely different frameworks that could one day supplant string theory. After all, scientific history teaches us humility. No ultimate theory is guaranteed, and bold assumptions often yield to new insights that overturn our established viewpoints. In the meantime, string theorists continue to refine their equations, searching for subtle hints and developing new methods that might bring the theory closer to the world we observe. Some have found partial victories, using string theory to better understand certain quantum phenomena or to shed light on strongly interacting systems. Others acknowledge that the journey is long and the road to experimental proof may still lie decades ahead. If you were expecting a swift and decisive resolution to our deepest mysteries, you might feel disappointment. Yet, if you are inspired, as Einstein was, by the allure of dedicating a lifetime to asking the grandest questions, then string theory, regardless of its current empirical standing, remains a rich, fertile ground for intellectual exploration. Science, in the broadest sense, is our tool to peel back the layers of the unknown. It illuminates the dark spaces of our ignorance with the light of understanding. Each answer exposes deeper puzzles, and every new theory generates fresh questions. Rather than concluding our inquiries, we are continuously at the threshold of new discoveries. In the vast cosmic landscape, where we have only just begun to scratch the surface of an immense unknown, the pursuit of understanding, be it through string theory or some other yet undiscovered framework, remains an essential, unending human endeavor.